Hi there, I'm back. I want to talk about first some of the homework from last night. I'm going to look at an error which was in the textbook on one of the questions and look at our formula for universal gravitation, and then I want to move on to looking at 5.4 and then going back to 5.1 and 5.2. Again, notice that there's only 3 notes in this whole chapter. It's a short chapter, which is why we've got a test plan for at the end of the week this week, on Friday. Now, if I look at question 24 in the textbook, it says calculate the gravitational field constant. Okay, calculate little g. Okay, we know little g is, it's 9.8, right? But it says, for the following planets. So on different planets, we know that the value of little g will be different because the mass of planets are different and because the radius of the planets are different. So if I'm going to calculate little g, I'm going to use my formula here. It says little g is equal to big G, the universal gravitation constant, times the mass of the planet, or the mass of Mars, divided by the radius of Mars squared. Now, this is where the problem is. When you put your numbers in, big G is 6.67 times 10 to the power of negative 11. The value for the mass of Mars in the textbook is wrong. They've given it to you as 6.37 times 10 to the 24th kilograms. That's not correct. The real number for the mass of Mars is 6.39 times 10 to the 23rd kilograms. Now, there's the mass there, divided by the radius of Mars, which is 3.43 times 10 to the 6 meters. I'm going to square it, and I come up with a G value on Mars, which is 3.61 newtons per kilogram, which is 10 times smaller than the answer in the book because they told you that this number here was actually 24 instead of being 23. Now, I want to actually take that answer, which is in newtons per kilogram, and say, well, hang on, I thought little g was measured in meters per second squared, because if we look at our equation for an object that's in free fall, again, we were talking about the parachutist who was going down yesterday, and I said the only force acting on the parachutist is Fg. If that's the only force, then that's equal to F net. And we know that if Fg is equal to m times g and F net is equal to m times a, then the masses of the person who's jumping cancel and a becomes g, where g is acceleration in meters per second squared. Think, well, hang on, where did that newtons per kilogram come from? Well, again, remember, what we know is that F equals ma, and that mass is in kilograms, acceleration is in meters per second squared, and our unit of force is in newtons. What that means is 1 newton, we defined a newton of force. Like, we had to decide how much force is 1 newton. Is how hard I push on the wall of the school. As hard as I'm pushing, maybe we'll call that a newton. And then everything less than that will be a fraction of a newton, and everything more than that will be more than a newton. So just like trying to come up with a standard kilogram, right, where everyone on the planet agrees what a kilogram's mass is, or what a meter's length is, we had to come up with what do we decide a newton is. And a newton is defined as the quantity of force that will accelerate a 1 kilogram mass at 1 meter per second squared, and that's what a newton is. Now, note here that if newtons are the same as kilograms times meters per second squared, then if I take this value of newtons up to here and plug it in, and newtons are equal to, let's scratch this out, and let's put in the other units for newtons, which are kilograms meters per second squared. And I look what I've got, kilograms in the numerator up here, and kilograms in the denominator down here, which can cancel out, and I end up with g is also equal to 3.61 meters per second squared. All right, so it doesn't matter which unit we use for little g. Right, little g is 3.61 newtons per kilogram, which means it will cause 1 kilogram mass to accelerate at 1 meter per second squared. Right, that's what our value for g is telling us. Okay, so that's how our units kind of all work around these two possible versions for little g. Now, one of the questions, question 30, says, compare the amount of time it takes for an object that's falling from a 553 meter height, which is basically the height of the CN Tower, to fall to the planet on Earth. So if I look at the CN Tower here on Earth, and I'm going to drop an object down, I can calculate the time that it takes because I know my formula for accelerated motion here, and I know that it's going to fall 553 meters down. V1 was 0, plus 1/2 the acceleration, which is negative 9.8 on Earth, times delta t quantity squared. Okay, and the answer turns out to be, I think, around 10.5 seconds, if I remember correctly. Now, if I do the same thing, if I was to build a CN tower on Mars, on the red planet, and I took the same object and dropped it on Mars and said, how long is it going to take to fall that same distance on Mars? Well, I'm going to get negative 553 delta d equals v1 delta t plus 1/2 the rate of acceleration, which is 3.61 meters per second squared down, times the time it takes squared. And I think the time it takes is something like 18.4 seconds, I believe. So notice that it takes almost twice as long to fall that same distance on Mars as it does on Earth, right? That's question 30 from the textbook. Now, the textbook goes through a fairly, you may or may not, I didn't go through, but you may have gone ahead and read the section in the textbook that talks about this concept of ratios. And when you're doing 28 and 29, it asks you to answer the question using ratios only. Ratios are an important mathematical skill, but I find for what we're doing here, I think it probably isn't worth spending the amount of time. I find a lot of people get really confused with ratios, so I'm going to just ignore them. So if I do 28a, right, and again, I'm not going to use ratios. It says to use ratios, so I'm going to go out on a limb here. It says, for this problem, use ratios only to determine the weight of a person at the following distances. Okay, so before I do 28a, let's go back to sections 5.1 and 5.2 in the textbook. So 5.1 and 5.2 are talking about this combination of terms here, mass and weight. Now, to most people in the world, if I said, what is your mass? You'd think, my mass? Yeah, what's your weight? What do you weigh? Right? And most people would use those two words interchangeably. Oh, my mass. Yeah, I weigh so many pounds or so many kilograms. I'd say, well, what is the mass telling me about you? Well, the mass is really telling me how much of you is there. Right? That's what your mass is. It's a quantity. It's how much of you is there, based upon the number of atoms. Every atom has mass, and the number of atoms that make up you, all 80 or 90 trillion atoms that are cells that are making up your body made up of their atoms, those atoms will make up your mass. Now, this word weight, okay, this is a word that is really misused outside of the science world, because a lot of people would say, well, your weight is what the scales tell you. Right? The weight is how many pounds or kilograms of you there are. Right? Your weight to a scientist is not your mass. Right? These two terms are two totally different things. If you asked a person who has a mass of 100 kilograms, what is your mass? I'd say, oh, my mass is 100 kilograms. But if I said to that same person, what is your weight? They'd say, well, my weight is 900, oops, shoot, come on, 900 newtons. That is my weight. No, that's a force. Exactly. Right, weight is a force. Weight is telling me how hard the planet is pulling down on you. That is your Fg. Right, so notice that mass is in kilograms and weight is measured in newtons. Now, that being the case, notice something else here that's going to be a bit of a problem. So if I go back, I was looking earlier, so this is a scale. Mrs. Bateman has one of these scales in her room, and notice that the units here are in newtons. They're not in kilograms, they're not in pounds. This is actually a Newton scale. When you stand on her bathroom scales, it will tell you how many newtons of force the planet is pulling down on you with. So again, if you're a 100 kilogram person, let's say you weigh 220 pounds, 100 kilograms, and you stand on these scales, it's going to go up to 980, right? Because at 100 kilograms, you have 980 newtons of gravitational force pulling down on you, right? So when you're measuring a person's weight, weight is actually Fg in newtons, and a person's mass is what you would expect it to be, which is measured in kilograms if we use the metric system. Now, that being the case, let's go back to the homework question I was just looking at for question 28. So question 28 in the homework says, use ratios only, I'm not going to do that, to find the weight of a person at the following distances. It says, assume the person's weight is 980 newtons on the surface of the Earth. What will be their weight when they are 3 distances from the center of the Earth? Not one distance, not on the surface, but 2 more distances away. So I'm trying to find the person's weight. And I know I can't just use mg because little g is going to change. As I get so far from the surface of the planet, little g is not going to be 9.8, so I can't use this formula here. I have to go to the universal formula, which always works. Now, so if I do my universal formula, I get that, where g is 6.67 times 10 to the power of negative 11. M1 is the mass of the person. Oh, well, hang on, I don't know the mass of the person. Well, I know that the person's weight when they're on Earth is 980 newtons. So on Earth, their weight is 980 newtons. That's given in the question. Oh, but their weight on Earth is mg, where g is 9.8. So m is 980 over 9.8. Oh, look at that. Person has a mass of 100 kilograms. So now I can go back to this formula down here, and I can continue by saying g m1 m2, there's my g, times m1, which is 100, times m2, the mass of the Earth, 5.98, times 10 to the power of 24. Okay, you're probably all starting to remember that mass of the Earth already, divided by the radius of the Earth squared. Oh, but I'm not on the Earth now. Now I'm 3 radii away from the surface of from the center of the planet. So I am 3 times 6.38 times 10 to the power of 6 away from the center of the Earth, and I need to square that number. And when I do all of that math, I get 112 newtons. So if I was standing on, assuming that I could just take those scales that I just showed you from the picture, and you stand on them on Earth, and it says, oh, you weigh 980 newtons on the surface of the Earth. If I could take those same scales up to that height above the surface of the Earth and have somebody hold them there with the scales sitting on their hands, and now you stand on the same scales, it would tell you you just lost a lot of weight. Right? You lost 870 newtons of your 980 newton force. Okay, so that word weight we've got to keep separated from the idea of mass. Okay, let's continue on here now. Now, let's think about a situation here where the person is in the bathroom, just got out of bed, okay, crazy hair going on, standing on the bathroom scales, and the bathroom scales say, let's say they're my scales. They say, and this is that 100-kilogram person. Check the scales, and it says, oh, this person is 980. Okay, and what is that telling me? It's telling me that the planet is pulling down on this body with 980 newtons. Now, if you can imagine for a minute taking those scales and you step off the scales, right, and the scales go back to 0. Then you step back onto the scales and they read 980. Okay, now think about what's going on here. When it's reading 980, right, the person is not going anywhere. Right, that person isn't going up or down. They're standing on the scales thinking about the shower. And as they are standing there, I know that there are two forces acting on this person. Right? The planet's pulling them down and the scales are pushing them up. Now, the scales are applying what's called a normal force. Okay, the normal force is always perpendicular to the contact surface, right, between the person and whatever they're touching. If I'm leaning against the wall is pushing back on my hand with a normal force. Right? The normal force is always a perpendicular force to the contact surface. Now, if I took that same person and I put a knapsack on their shoulders that had a mass of 10 more kilograms or about 100 more newtons of weight, and they now go up to 1,080, what those scales are going to read now is 1,080 because the planet is pulling down on the person and their bag knapsack with 1080. The scales are pushing back with 1080. What the scales are telling me here is how hard they are pushing on that person. If somebody was sitting on this person's shoulders, okay, you got your little sister, little brother sitting on your shoulders, and now you weigh even more, the scales have to work even harder to push back on you, right? And as such, the FM will go up even more. So what your scales are they are the normal force. They're showing us the contact force here between the object and whatever it is that's touching, and it is always perpendicular to the contact surface. So if I look at some object that's resting on a horizontal surface, so let's say here's the floor and here's a crate sitting on the floor, right? If I was to do a free body diagram of the crate, okay, so let's erase the floor. Okay, now I say, what are the forces acting on the crate? Planet and the floor. If I've got a fridge magnet on a vertical surface, so this is the trickiest one of the day. Okay, so here's the side of your fridge, and here's the fridge magnet. Right? I say, what are the forces acting on this fridge magnet? Well, I know for sure the planet is pulling it down. I know for sure that there is a magnetic force in the magnet that's pulling it onto the surface. Let me get rid of that fridge for a minute because I want a free body diagram. I want to have just the body itself. It's being pulled this way by a magnetic force which is pulling it onto the fridge. Sometimes, if you buy a cheap fridge magnet and you put it on the fridge, it'll slide down the fridge. And the reason why is because gravity is pulling it down, and there should be some friction here which is preventing it from sliding down the fridge. Right? Friction is the key here. If you take your fridge magnet and you take it off the fridge and you spray your fridge magnet with PAM or some kind of cooking oil and try and put that magnet back on, it's just going to slide right down because you have got rid of the friction. Right? So the friction is working that way, and the question is, what is the normal force here? It is perpendicular to the contact surface. So while that fridge magnet is sitting there, say you've been to your favorite spot in Miami or in Orlando or Daytona or Bahamas or wherever you go for holidays, and you bring back your fridge magnet and you're sitting there looking at it on the fridge, there's four forces, right? The planet's pulling it down, right? Friction is keeping it from sliding. It is sticking on the fridge, and the fridge is pushing it back. And all of these forces will cancel themselves out so that hopefully the magnet doesn't go anywhere. Okay, so those are all the forces that are acting here in 5.4, and going back to 5.2, which is looking at the difference between mass and weight. Okay, so I want to take 1 minute here and just look at these two samples, and then I'm going to leave you with these questions here on page 165 and page 182. All right, so I'm looking at the samples on page 163 in the textbook. So the first sample says, for a person of mass 40 kilograms sitting on a box, what is the normal force? What is the value of the normal force? Okay, so here's the box. Here's the person sitting on the box. Okay, and I say, what are the forces acting on that person? Well, again, if I was to get rid of the box, you don't need to get rid of the box. If I was to get rid of the box and now put in the forces that are acting on this person, I would say the earth is pulling the person down and the box is pushing the person up. Those are the only two things that are acting on me while I'm sitting on that box. Planet's pulling me down. I'm not going down because the box is keeping me up. Now, I know that Fg for this 40 kilogram person is 392 newtons down. So therefore, my normal force has to be equal to that. Because I know that F net, which equals ma, which equals 0, because acceleration is 0, is equal to Fg plus Fn. And if I know that Fg is negative 392, I know that Fn will be plus 392 newtons, or 392 newtons away from the surface, right? It's a normal force. It's perpendicular to the surface that I'm sitting on, perpendicular to the top of the box. Okay, so there's sample number 6, and then sample number 7 in the textbook. This one's on page 164. Okay, it shows a picture of a person sitting on a box, and the crane is lifting the box up, and the crane is exerting a force of 92 newtons. So if I look at here's the crate, here's the person sitting on the crate. This is a really contrived question. And that there is, a friend is now trying to lift the person's hand using a crane, sitting on the box. And the question is, what is the, okay, so there's a harness now around the waist of this person. Let me go to a different color if I can. Let's say blue. I've got a harness around my waist, and it's attached to an upward force on the crane. So the crane is here causing an upward force. Of 92 newtons. Okay. I know that while I'm sitting there, I know that, let's change back to black now. I know that there's an Fg pulling me down. Come on, you. and we calculated that number, whoops, in the last question to be 392 newtons. I believe. Yep. And the crane is pulling up with 92. Now, what's happening is, again, the question is not terrifically well worded, but it's basically saying the person isn't moving, because even though the crane is pulling up with 92, the planet's pulling down with 392. The crane isn't strong enough to lift this person off the surface of the box. So if I draw the F net statement now, I say the F net is equal to three forces. Gravity's working, the box is working, and the crane is working. And F net for, acting on the body is MA. Right, MA is the person's, well, it doesn't matter because there's no acceleration. FG was negative 392 plus the normal force, whatever that is, plus the crane force, which is plus 92. So I've got negative 392 and plus 92, so I end up with negative 300. I'm going to move them across to the other side. And I will get an Fn equal to plus 300 newtons. That would be the normal force. So if that box could only support 350 newtons of weight, and I'm sitting on it and I'm 392, I'm going to fall right through that box. I'm going to crash it. But if that crane is giving 92 newtons of upward force, then I'll be able to sit on that crate even though it can't handle my whole mass, because the crane is going to offset some of the upward force that the normal is trying to create, right? And the crane will help with that. Okay, I will finish there and leave you with questions on page 165 and page 182 here. And then tomorrow when we come back for our last note, we will do this note here on the types of friction, and then we will finish chapter 5. And that's the entire chapter. So notice that we've really largely only done a couple of things in this unit. We've looked at, so far, Fg equals mg. We've looked at Fg equals big G m1 m2 over r squared, and looked at the value of big G, the universal gravitation constant. We've looked at little g on Earth and little g in other places. And now we've started to look at this normal force, and we're going to use that normal force tomorrow when we start talking about friction.